Hello, and thank you for joining us on Space Nuts, where we talk astronomy and space science. Great to have your company once again. And coming up on this particular episode, we're going to talk about an exoplanet that has unusual rain. It's raining gemstones and ruby slippers. Well, maybe not the ruby slippers, but definitely gemstones, which is very unusual. We're going to do a James Webb Space Telescope update, which is something new for us. And a quadruple asteroid system has been discovered by a group of people in Thailand. So that's fascinating. We'll also be answering some audience questions. Bob wants to talk about research papers and how accurate or otherwise they might be. Al is asking a question about a black hole becoming a singularity, and is that possible, because he doesn't think so. And Steve is asking questions about photons and black holes. We're starting to leak back towards the black hole phenomenon, starting to dominate again. That's all to come on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
My name is Andrew Dunkley. I am your host. Thank you for joining us. And with us again this week, because we can't get rid of him really, it is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. How are you?
You are the Space Nuts barnacle. You are. That's
I know. Just a barnacle on the backside of Space Nuts. Dear. Oh, well. It was ever thus. Yeah. I've been a barnacle. In fact, I'm probably still a barnacle on the Department of Industry, Science, Energy and Resources as well. They can't get rid of me either.
Yeah, why would they want to, Fred?
Oh, thank you, Andrew. That's a nice comment, yes.
Right, we've got a lot to talk about today, so let's get straight to our first topic. And this is a really interesting one. We've talked about exoplanets and even planets and moons in our own solar system that have unusual kinds of rain, like sulfur rain and acid rain. And I think we talked about a planet once that rained diamonds. Now there's an exoplanet that rains gemstones. What's this all about?
Well, yeah, it's gemstones among other things, and it's there's a lot going on this exoplanet. What is it? Well, it is. I think it's a WASP. Yeah, WASP 121b. WASP is a project that detects exoplanets by the transit method, the fact that their brightness drops when they pass in front of their parent star. WASP 121 is actually a star which is about 850 light years from here. It has a planet which is very close to it. It's a hot Jupiter. That's the the official description, because it's a big planet, and it orbits its parent star once every 30 hours. So, its year is 30 hours long, Andrew. It just beggars belief, doesn't it? But that's what's happening. Now, that means one of the things that means is that with a period that short and the distance between the parent star and the planet that small, this planet will be tidally locked to its parent star, and that is the key to understanding what's going on here. It is its day side always is permanently facing the parent star. Well, that's a bit of a tautology, really, isn't it? Because the day side is always facing the parent star. But the bottom line is, this is a good start this morning.
You're going well, Fred.
The bottom line.
See how I bailed you out of that?
Yes. Oh, well done. Thank you. Yes. The planet is rotating at the same rate at which it revolves around its star, like the moon is rotating at the same rate as it revolves around the Earth. And so you've got this one side of it that permanently faces the heat source. And that means one side is hot and the other side is cold. Now, given that we can't see these planets directly, you may well ask, Andrew, how can you study the day and night sides of a world like this in detail?
That's a good question. Glad I thought of it.
I'm glad you thought of it too. The answer is it's really clever stuff and needs, it needs really quite significant astronomical infrastructure in order to make these observations. I should mention that the authors of this work come from MIT, Massachusetts Institute of Technology, Johns Hopkins University, Caltech, and other US universities.
It is a mouthful, but it is Massachusetts.
Massachusetts is what I tried to say. That's right. I didn't really. Anyway, never mind. I didn't do well with it. But so how do you detect what's going on the day and night sides of a world like this? And what you do is you observe the planet, and all you can see is the star. That's the only thing that is visible in your telescope.
Yeah.
But you observe the star's light throughout the orbital period of the planet. And given that that's only 30 hours, you don't have to wait very long. If you were looking from outside the solar system and trying to do this with Jupiter, you'd be waiting, 12 years or something like that? It's much longer. No, I think it's 5 years. Sorry, I should do that calculation again. Anyway, 30 hours gives you time to actually work out exactly what's going on through the different phases of the planet, because that's what it's all about. It's like the phases of the moon. We watch the moon going round because it's lit up by the sun, and we can see, it progressing from new moon to first quarter to full moon and all the rest of it. And you can do the same thing with an exoplanet, but all you're able to measure is the total light from the planet plus the star. But as you'd imagine, that varies throughout the revolution period of the planet. When the planet is behind the star, all you've got is the light of the star. And I should add that you're not just observing how bright it is; you're also observing the spectrum of this thing. So you're looking in detail at the chemical constituents that is revealed by the light that is coming to you. Yeah. So when the planet's behind the star, all you're seeing is the light of the star. When the planet shifts slightly in its path around the star, so you can see both, what you've got is effectively you're looking at the full planet, like an equivalent of a full moon. It's almost completely illuminated. Right. And that light adds to the light of the star. And so you can then look at how the spectrum has changed. And that is telling you about the atmosphere of the planet itself rather than the atmosphere of the star. In fact, what you can do is subtract the star spectrum from the spectrum of the combined planet plus star, and you get the planet spectrum. That's how this works. And then that changes throughout the planet's year, 30 hours. And eventually you're looking at the backside of the planet. And in fact, you have a point where that is superimposed on the star. Once again, you can do some clever work, because you can look at the combined spectrum of the backside of the planet superimposed on the star itself. That combined spectrum, if you subtract out the spectrum of the star itself, it shows you what chemical constituents, again, are in the atmosphere of the planet, because the light of the star is passing through the atmosphere of the planet, round the edge of it, and coming back to Earth. So that's the technique. And what's been found is that this object is quite extraordinary. So it's got a day side that is extremely hot, more than 3,000 degrees Kelvin. So what that does is it's known that there is water vapor in the atmosphere of this planet. Well, there's water vapor on the night side, but on the day side, the water molecules are just torn apart because of the high temperatures. So you've got hydrogen and oxygen atoms that are they're independent within the atmosphere. And then it turns out that because of the heat, that generates high pressure in the day side, which causes winds that blow things around to the night side. And on the night side, it's cool enough, for these things to form back to water. And so you get water vapor forming in the atmosphere of the dark side of the planet. They estimate that these winds are 5 kilometers per second. Ooh. So this is 11,000 miles per hour. It's 16 or 17,000 kilometers per hour.
Sounds like that's the same as it was in Sydney yesterday.
Yeah, we didn't get the wind, but we got the rain. So we got the water vapor. Huge quantities of rain. Oh gosh, bucket loads of it. H2O suitably combined back into water vapor.
Yes.
So that's what they get on the dark side of this WASP 121b. But wait, there's more. Because it's not just water that's circulating like this. They find that on the night side, the temperature is right to have quite, I guess the best word is exotic, clouds of exotic materials, and iron is one of them, and a mineral that actually is a constituent in gemstones. That's the point that you were making right at the beginning.
Yeah. Well, that's the journalistic hook, isn't it?
It is, absolutely. So, yes, to quote the physics.org report on this, on the way around, exotic rain might be produced, such as liquid gems from the corundum clouds.
Wow.
So, liquid rubies, that'd be quite nice, actually. Well,
yeah.
Anyway, really quite remarkable stuff. I should mention that these observations were made with the Hubble Space Telescope. It was one of the spectroscopic cameras on board the Hubble telescope that was used, and fantastic work. Congratulations to the team and to the journalists who are writing about this.
I don't suppose they can tell us exactly what kind of gemstones these might be, or gem
blobs
components.
Yeah. They're suggesting that it could be maybe. Look, I had rubies in my mind, and maybe rubies and sapphires. That's the possibility. Corundum apparently is a mineral that goes towards these gemstones.
So I wasn't far wrong with my ruby slippers analogy.
No, it's a very nice one. I like that very much, yes.
Interesting. All right. That's a fascinating discovery. And if you want to read more about it, you should go to the phys.org website. That's not FIZZ, that's phys.org website. It's a fabulous website if you want to catch up on that and many other stories. Now, while we're still up in space talking observations by telescopes, there's one called the James Webb Space Telescope that popped up in the news recently. I haven't heard much about it, to be honest, but they've been trying to sort of put it all together and get the parts all linked up and get that mirror all organised. They've been taking some test photographs. We talked about one last week with the star that came out in 18 images. Has there been any progress since then?
There has, Andrew, yes. And it's part of the process of, harnessing this mirror from 18 segments to a perfectly focused single surface mirror, making beautiful images of different distant objects. So what we saw last week was 18 images of a star in the constellation of Ursa Major in the Northern Hemisphere, which were completely randomly placed in the field of view of the camera. And that was great because all 18 were there, so that the mirror segments were somewhere near where they ought to be. What they've done now is they've tidied that up so that you've got this lovely hexagonal pattern of these 18 images. And doing that actually expedites the process of, first of all, focusing each of the segments independently to give you a perfectly sharp image, and that will still result in this display of 18 different images in a hexagon, but that hexagon will kind of match the positions of the mirrors that have formed the image, if I can put it that way. It's just a ready way of identifying which star has come from which segment. When they've focused all the segments, you'll get perfect star images from each segment, and then the work will begin to bring them all together so that they make a single image. That's the final stage of the process.
Yeah, I'm looking at the image compared to last week's, and you can see the improvement in the alignment. They're really starting to come together well.
It's great. The process is called segment alignment, and the final stage, when they've got that right, and each star is focused, or the star from each segment is focused, then they do what's called image stacking, which, as its name implies, they put all the 18 image segments on top of one another to make a single image.
Mm. Well, I know a bit about that. I haven't tried it, but a few people I've been chatting with about astrophotography of late have been telling me about some of the methodology that they use, and image stacking. Some of them actually take, rather than photos, they take videos of the images, and then they work that into a still picture. Using the data that they've built up. There's some clever people out there. I'm not one of them, but
well, you are. You're following in their footsteps.
I'm trying to. Some of it I find way out of my league, but I'll catch up eventually.
That technique. So what you do is you take a video, which consists of many still frames, and this is mostly for observing planets. Actually, I have to say, and what's happening during that period is we're not talking about the James Webb now, folks. We're talking about Andrew's backyard. But the atmosphere varies, and occasionally within that video there will be images where what we call the seeing, the amount of turbulence is virtually zero. So there's the perfect image, essentially. So what you can do is you extract the perfect images from your video and then stack those together. And you get almost a what we call a diffraction limited image. And I might just add that technique, which is called lucky imaging, was invented by a friend of mine by the name of Craig Mackay at the University of Cambridge. He did this on professional telescopes 25 years ago. And his lucky imaging process is now basically carried out by amateur astronomers because he can do it. Fabulous stuff.
Fantastic. It's well named too, because it makes sense that if you take a series of stills, within a few seconds, you could have hundreds of images, and because 30 frames per second is about average these days, isn't it?
That's right. Yeah. So you're going to have thousands of images, of which
you're going to get lucky.
Yeah.
In that regard, rather than taking, like my camera takes 5 shots with I've set it up to take 5 shots of a single press, and I could get lucky there too, but probably not as lucky. Makes sense. Yeah, it's good. And I should have known that you'd be connected to somebody who came up with the idea.
Yeah, I'm afraid that's right.
All right.
It's a small world is the astronomy world. That's the answer to that.
Yes, I imagine so. Sorry, small world talking about a very, very big world.
Big universe,
indeed. Yes. This is Space Nuts with Andrew Dunkley and, of course, Professor Fred Watson. As you know, online security is all important these days. There are lots of people out there that are trying to swindle you out of your money, and a lot of them use hacking as a way of doing that. And I've heard some real horror stories, even in the last couple of weeks, about people who have found money disappearing from their bank accounts or their credit cards being used that they didn't know about. It's pretty rough stuff, and it's not fair, but it's also a reality of the modern world. So how do you protect yourself? Well, you use a virtual private network like I do. NordVPN is probably the best in the business. It's certainly fast. It's certainly efficient. It's available all over the world. They have servers in multiple countries and easy to access. And it gives you all sorts of benefits. For a start, if you are using your mobile device in a public Wi-Fi scenario, you are exposed unless you use a VPN. And NordVPN works on tablets, it works on smartphones, it works on laptops, it works on computers, it even works on smart TVs. So it gives you that great wall of protection. And look, they've got a lot of endorsements from major organisations around the world because they are so very good. The BBC, Forbes, BuzzFeed, Huffington Post, Wired, they all point the finger at NordVPN as being the best in the business. It also comes with a 30-day money-back guarantee. So if you buy it and you don't like it, you can say, no, sorry, this is not for me. And I do want to actually congratulate our sponsor, NordVPN, because they're about to turn 10. In fact, 10 years is in the internet world is a great achievement. So congratulations to NordVPN for 10 years. You certainly are a success story if you've racked up a decade. Now, as a Space Nuts listener, of course, there is a special deal for you, and you can get it by logging on to nordvpn.com/spacenuts and check out the deal. In fact, they're offering 72% off a 2-year plan at the moment. And they're going to be offering little presents to celebrate their 10th birthday. So it's a great time to take advantage of this offer as a Space Nuts listener. So log on to nordvpn.com/spacenuts for your special deal with NordVPN. You won't regret it. It is a great service, and it is certainly going to give you peace of mind when you're browsing. It also gives you the ability to get past those geo-blocking situations if you want to log onto a website in another country that has maybe an article you want to read or a TV show you want to watch or something like that, and they say, sorry, you're in the wrong geographic zone. VPN can get you around that. There are all sorts of benefits to having a virtual private network. So check it out today by going to nordvpn.com/spacenuts, using the Space Nuts code for your special 72% off 2-year deal as a Space Nuts listener with a 30-day money-back guarantee. Now, back to Space Nuts.
3, 2, 1.
Space Nuts.
Now, if you would like to do us a favour, that would be wonderful. You can send your checks to Fred Watson of course, if you do want to become a patron, you can do that, and that is putting a little bit of money into the kitty to keep the podcast rolling, which you can do via our website. Now, that is totally optional, and thank you to those many patrons that do so through Patreon or Supercast. So that's something that you can do, or you can make one-off donations through the buy us a cup of coffee button on our website, spacenutspodcast.com. Or if you want to do something that's going to be cost-free and just cost you a bit of time, write a review through whatever podcast platform you happen to use. So that's very helpful as well. So those are some of the options to help support the Space Nuts podcast, and we do appreciate anything anybody does to keep us up and running. Now, Fred, we have a very interesting story out of Thailand, which I found most surprising. When you talk astronomy and research and discovery, you don't generally default to Thailand. A beautiful country. I've visited it, and lovely, lovely people. They're some of the nicest people on the planet, to be honest. But a few researchers from the National Astronomical Research Institute of Thailand have announced this discovery. Now, this is sort of a new spin on an old discovery from what I've read.
Well, yeah, that's right. It's a new discovery. Yeah, Thailand's actually got quite an active astronomical community, Andrew. I have colleagues who, in fact, one in particular who works there, and a number of others who've been there working. This is 3 researchers, one from Thailand, 2 from France, at the Université de Lyon and the Université Sorbonne.
Righto.
Yeah, the Sorbonne.
That's pretty good, Fred.
In Paris, yeah. We aim to please. Anyway, what they've done is they've used the Very Large Telescope down there in Chile, which is, of course, operated by the European Southern Observatory, and to which our Australian astronomers also have access because of the strategic partnership that was signed back in 2017. I've always got to plug that, and it's great. It's excellent that we've got that. It's amazing to think that strategic partnership between Australia and the European Southern Observatory is now halfway through 2022. It's staggering how fast time flies by when you're having fun. Anyway, back to this asteroid. It is a well-known asteroid. It's number 130. Electra was discovered back in 1873. and it's been known actually for almost 20 years that it had at least one moon. That was discovered in 2003. Another one 11 years later in 2014, and now another moon. So this is it makes the asteroid a kind of quadruple object because it's an asteroid which is relatively large. It's 260 kilometers across. It's a decent-sized object, but it has 3 moons. So altogether, it's a quadruple object, having 4. What staggers me about this, Andrew, is just the fact that these scientists have been able to observe these moons because they are a long way away. This asteroid is actually in the outer region of the main asteroid belt, so it's not a particularly close one. It is something called a G-type asteroid, and they're quite rare. In fact, they're carbonaceous asteroids, which are relatively common. But these are a particular subgroup of those, and it's about 5% of all asteroids are G-types. And in fact, the most notable and the biggest is Ceres, the dwarf planet Ceres, which was the first asteroid to be found. So what I was going to say was, what is staggering, given how far away this object is, Electra, is how small these moons are. First moon is reckoned to be 6 kilometers across. The second moon discovered is reckoned to be 2 kilometers across. And the third one, the one that's just been discovered, is actually 1.6 kilometers across, about a mile. It's very, very small. And when you think something, a mile across at that distance, the far edge of the asteroid belt, that is astonishing stuff. So it's really extremely good work. They've done a lot of clever image processing, but the moon is definitely there. Actually, I found a statistic which I thought was quite remarkable. This little object, the new one, is very close to Electra. Its orbit's quite close to the asteroid itself, and its brightness is 15,000 times less than the brightness of the asteroid. Wow. So you've got something. It's the old comparison of trying to spot the cigarette end of the lighthouse keeper while he's on the platform next to the lighthouse. It's that sort of huge difference in brightness. So they've done very, very well to tease out the light of this little moon orbiting around asteroid Electra.
And Space Nuts does not endorse smoking.
No, it's a difficult. I tend not to use that.
I know, I was just joking.
But it's hard to find a better. It's a really good. It's a really good example. Yeah. Arthur, don't worry. I'll think of something.
Maybe a torch or.
You could say is mobile phone.
Mobile phone light. Yeah.
Yeah, the mobile phone. That's it.
No, I understand what you're saying. Makes sense.
Yeah.
Now, I just need to clarify something in my head because I get confused about this. When you say the asteroid belt, this is out beyond Mars?
Yeah, the main belt is between Mars and Jupiter. That's correct. So, and this is on the far edge of that. So it's, its distance is really quite significant.
Because the other one's out around, it includes Pluto, right?
Yeah, that's right. That would be the Kuiper belt or the trans-Neptunian objects and all the different categories of objects that are out there. But yeah, it is a very distant asteroid belt. So I guess the 3 main regions where there are asteroids are, first of all, the main asteroid belt, and that is by far the most populous. And then the Trojan asteroids of Jupiter. These are the ones that orbit in Jupiter's orbit and in front of and behind Jupiter. And then, the trans-Neptunian objects, the objects way, way out in the furthest reaches of the solar system.
Yeah, so there's all these layers in the solar system that sort of live in little regions as you spiral out. And
that's right.
So we've kind of got a divide between the rocky planets and the gas giants, haven't we?
Yes, that's right, and that's exactly right. And it's once again, it's because Jupiter's such a big planet. It's probably. The main asteroid belt is remnants of the formation of the solar system. And they've kind of been steered there just by the gravitational influence of Jupiter. It's probably more or less where they form, but they're still there. Jupiter's huge gravitational pull may well have inhibited the formation of another planet there.
Yeah.
So we've got this debris.
It sort of reminds me of flat pack furniture, Fred, because the formation of the solar system, and they've got all this leftover stuff. When you get flat pack furniture and you put it together, you go, hang on a minute,
Where's that go?
What am I supposed to do with this?
Yeah.
Where does this go?
Yeah, and when you realise where it should have gone, you're really too far down the track to take it to bits. And
Don't worry about it.
Yeah.
If we ever move, I'll fix it then.
More or less, yes, that's right. Put it in the box and forget about it.
But yeah, what a great discovery, and delightful to hear that there was involvement in Thailand, because I don't think too many people would realise that they've got an astronomical fraternity, if you like.
Yeah. Yep.
This is Space Nuts, Andrew Dunkley and Fred Watson. Let's take a little break from the show to talk about our sponsor, Magic Mind. Now, I introduced you to this product a couple of weeks ago. This is a liquid. It's a for want of a better word, a conglomerate of natural products that are designed to improve your thinking and to take your reliance away from getting that kick start at the beginning of the day with coffee. Not that they're telling you to stop drinking coffee, but the fellow who came up with this concept, James Webb, was drinking a lot of coffee, and he had health problems as a consequence of that. And he thought, there's got to be a better way. There's got to be something else I can do to sharpen my thinking. Now, he worked in Silicon Valley, was highly successful, and the side effect of that was, to keep himself motivated and going, because he worked very hard, he drank a lot of coffee. I think I heard him say something like 12 cups a day, some astronomical number, and it was not good for him, and he started having heart problems. So he thought there's got to be a better way to get the brain working, get your thinking better, getting you in a position to concentrate more, be more focused, be sharp. And so he worked with a team of researchers and scientists and nutritionists and put together a product that he calls Magic Mind. And he sells it in little shot bottles. They're so cute too, by the way. Packets of 14. And I've been trying it for the last couple of weeks. I was really keen to see how it went, particularly with my golf, because golf is a thinking game. Now, I've been on it for 1 week, taking a shot every morning with my cup of coffee, which is what they recommend. If you want to still drink coffee, drink your coffee and take a shot of Magic Mind while you're at it. And has it made a difference to my sharpness and my thinking? I believe so, particularly in light of the fact that I do morning radio, breakfast radio, and, you've got to have your wits about you early in the morning, and sometimes I don't. But I have noticed in the last week or so on the air that my brain has been more alert after taking my shot of Magic Mind. And one of the things, I know this is going to sound strange, but one of the things I've generally had trouble with throughout my career is when I'm telling a story and I need to come up with a punchline, because I tend to work on the fly. I don't sit down and write and research and do a lot of preamble before my show. I tend to do it on the fly. I like to stay up to date. If something breaks, I want to talk about it straight away. Quite often I tell stories and I like to sort of hit a punchline at the end, and quite often I struggle to come up with something that works. This week, surprisingly, I have had no problem with that. Is it a coincidence? Maybe. I like to think it's because my brain is functioning better. And I've come up with some real rippers the last couple of days. Floating my own boat a bit here, but I do enjoy my radio, and I do love to come up with one-liners. And sometimes, in fact, a lot of the time, I haven't been very successful in that regard, and I tend to let it slide. But this week's been extraordinary to a certain degree. Now, did it help with my golf? Well, I'd only had a few shots of it up until my most recent golf round, but I will say I did have clarity of thinking. I did make good decisions, but it doesn't reflect in the score because golf is that kind of game. I had what I would consider personally a poor result, but it wasn't because of my thinking. I just played bad shots, but I was trying to do what my brain was telling me to do. I listened to myself. Most striking, though, is I didn't get frustrated. I didn't get upset. I didn't let anything bother me. And I think that's because my brain was functioning better. And that's really important in golf. So I think, to be totally honest with you, and I said from the start, I would be dead set honest up front, this is working for me. This is definitely something you should try. Now, as a Space Nuts listener, we have a special URL set up so that you can read all about and learn about this amazing product called Magic Mind. You can check out what's in it. There are things in there to improve blood flow and cognition. There's a lot of research gone into this. It's not sort of some weird off-the-shelf thing that somebody's cooked up. It's there's definite science behind this. So go to magicmind.com/spacenuts to find out more. And as a Space Nuts listener, of course, there is a special deal. You can get 10% off. And they're calling it the Gatorade for creators. So Creatorgade is, I reckon that's, or Creatorade is what they're calling it on their website, which I think is very clever. So if you want to learn more about it, it's magicmind.com/spacenuts. And as a Space Nuts listener, there's a 10% off deal available right now for this product called Magic Mind. And we'd love to hear from you as to whether or not you think it's working for yourself. I certainly feel much more alert and much more awake during the course of the day. And I think I am thinking better as a consequence of trying this out. I've got another week to go, so I'll give you an update next week and see how things are progressing. But magicmind.com/spacenuts. And you never know, it might just make a big difference in your business and personal life. So try it today, magicmind.com/spacenuts, and let us know how you go. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Okay, Fred, let's get into our question segment. This is where people who listen to Space Nuts send us all sorts of hyper-intelligent questions that I've got no clue about, but Fred has an inkling. And our first one comes from Bob.
This is Bob from Asheville, North Carolina in the U.S. I have 2 questions. In 2005, Professor John Ioannidis published a highly influential paper in PLOS Medicine titled, "Why Most Published Research Findings Are False." He makes the argument, and here I'm quoting, that for most study designs and settings, it is more likely for a research claim to be false than true. It's important to note that he was focusing on medical studies, which have less scientific rigor than physics. He does, however, conclude that, and I'm quoting his paper again, that for many current scientific fields, claimed research findings may often be simply accurate measures of the prevailing bias. My first question for Professor Watson is, how often does this happen in your field? Meaning, how often are published research findings actually false because of bias or statistical reasons? My second question is a hypothetical. Medicine changes relatively quickly. For example, peptic ulcers were treated with surgery until 1984, which is when Barry James Marshall, an Australian physician at Royal Perth Hospital, reported that peptic ulcers were caused by a type of bacteria called Helicobacter pylori. Today, ulcers are treated with antibiotics. Professor Watson, suppose you could fast forward 100 or 500 years into the future and look back at cosmology and astro.
And that's where Bob unfortunately got cut off, but we think we've got the nuts and bolts of his question. So we're going to take a stab at it for you, Bob. But yeah, I guess the first part of his question is about scientific papers, research papers, published works, and how maybe they could misinform or not be quite accurate. Is that something that happens?
Look, it's a really interesting question. There are, I don't think there in astronomy there is a strong incentive, perhaps, or reason why people should intentionally misinform. I think that is almost always zero. And what research that does bark up the wrong tree, what research of that kind that there is honest mistakes.
Like the color of the universe, perhaps.
Yeah, well, that's right. That was an honest mistake. Yeah, which was what was it? It was kind of.
They originally said it was aqua, but it turned out to be beige.
It was beige. That's right. And in fact, I remember when I read that paper. This is probably 10, 15 years ago, and I know the guy who wrote it quite well. I remember when I read that paper thinking, this cannot be the case. You can't have an aqua universe because it's expanding, and you've got basically a redshift there, and it turned out to be beige, which is redshifted aqua. Anyway, look, the kind of thing that I was thinking of, Andrew, and it might go to the heart of Bob's question, is you remember last year there was a big fuss when people thought that phosphine had been detected in the upper atmosphere of Venus. And phosphine is on Earth is generally produced by biological processes. And so I know that the researchers who did that work, and I know some of them, in fact, I talked to one of them afterwards. He's a friend of mine in Hawaii. They were very, very careful to tease out the signal of phosphine from the noise. This was done with quite big radio telescopes. In fact, ALMA was one of them, the Atacama Large Millimeter Array. It was with reluctance that they mentioned the fact that phosphine's a live product.
Because the popular press jumped all over that.
Yeah, that's right.
There's life on Venus. There's life on Venus.
Yeah, exactly what happened. And, maybe the bias that Bob mentions is there because it's something that we're all kind of trigger happy with. We are urgently trying to seek any evidence of life anywhere else in the universe. Now,
and when you give some elements of the media an inch, they take a mile. That's
true, and that certainly happened in that case.
Yeah.
My recollection is that the original team still stand by their discovery that it was phosphine, but there was another paper published. It must have been actually the year before last when the phosphine measurement was made, because I think it was early last year that another paper was published showing how the phosphine signature could be mistaken, that it might actually, I think it was something like nitrous oxide. I can't remember. It was something a lot less suggestive of life processes. So I think honest mistakes are made, but yes, there might be a bias there too.
Generally, you'll probably find bias in circumstances where somebody's trying to sell something.
Yeah,
you might get those, studies that are released into certain products that improve your life, and the study turned out to be 10 people at a 5-star resort for a weekend answering a questionnaire.
Yes,
that kind of thing. So there's a bit of that goes on.
There is certainly less so in astronomy. Astronomy, I think, is partly one thing you're looking for, and you always check this whenever you make a discovery, is how consistent it is with what we already know about the universe. Because often, our discoveries, they're highly forensic. It's all done at distances ranging up to 13 billion light years. Just turning to, and I'm hypothesizing here as to what the second part of Bob's question was, because he got cut off, as you said. But I think he might have been wanting to ask me, what if I fast forwarded 100 years into the future and then look back at 2022, what I would think of as being discoveries that maybe were misleading. And perhaps the one that comes to mind, and it's not through any lack of honesty, this is the best evidence we have so far, is that dark matter exists and that it is a subatomic particle of some kind. That is pointed to through so many different experiments, and there's a self-consistency about it as well with what else we know about the universe.
Yep.
But it could well be that it turns out that it wasn't that. That in the end, there is something that we don't understand about physics. And what I'm thinking of is MOND, Modified Newtonian Dynamics. We've got a friend out there in the audience, Peter Verweyen, who's studying that for his PhD and doing a great job. Just maybe the tide will turn and people will see the evidence for modified Newtonian dynamics, which means that gravity doesn't behave quite the way we thought it did on large scales, that might turn out to be the answer. That would be one I might venture to suggest would be something that in 100 years' time we might look back on and say, we all thought it was dark matter. Yeah, how foolish were we?
Yeah, no, and that's probably not an uncommon scenario. I mean, we hindsight is 20/20, and
yes, that's right.
You don't have hindsight until you go forward and look back and go, okay.
All right, that was it. That was why.
Yeah.
Yes. Yeah.
Mm. Of course, we get it right a lot of the time too.
I think we do. I think that's right.
All right, Bob, lovely to hear from you. Thanks for your question. Let's move on to our next question from Al.
G'day, this is Al on the Sunshine Coast. G'day, Fred and Andrew. Given that the centre of a black hole is almost infinitely dense and mass slows time, surely a black hole cannot have had time to reach a singularity. The universe is not old enough. Thanks for the best podcast on the net.
All right. Thanks, Al. And thanks for the endorsement. That's lovely. I thought it was the best one in the universe. But anyway, that's the way it goes. Now, interesting question. A black hole can't reach a point of singularity. What, has anyone ever hypothesized that could be the case?
No, because time dilation is a phenomenon that depends on the reference frame that you're in, Andrew. It's like, I mean, this is gravitational time dilation. So we on Earth see our clocks ticking at a normal rate, whereas we know that actually relative to what's going on outside, they're slightly slow because of the gravitational pull. But it's that relativity between the two. So the black hole itself just sees time progressing normally. It's only to an outside observer that you see it highly dilated because of the gravitational pull. So, yeah, it probably does have time to contract to a singularity.
Aha. There you go, Al. A short, sweet answer. Sometimes they're simple. But, yeah, interesting thought on your part, no doubt about that. And we're going to squeeze in one more question today, and that comes from Steve.
Hi, Fred and Andrew. This is Steve from Sydney. First off, thank you for your amazing podcast. I look forward to it every Thursday, so thanks again. I have two questions. Firstly, if photons are massless particles, why are they affected by gravity? And secondly, and I apologise in advance because it's a black hole question, when a spinning star collapses to a black hole, how is angular momentum conserved? How is the spin given to a point with no dimension? And I guess an intermediate question is, if the collapse takes a finite amount of time, then at some intermediate stage while it's collapsing, what happens to angular momentum? It would seem to me that as the star collapses and becomes smaller and smaller until it finally sort of becomes a singularity, that the speed would increase. And really, I can't see why it just doesn't keep the speed doesn't keep increasing until it becomes infinite, which it obviously doesn't do. So I look forward to your explanation. Thanks once again.
Thank you, Steve. Thanks for the question. That's a really good one. Did you take notes, Fred? Because there was a lot to that.
The first part is about photons being massless particles. They're massless in the sense that they don't have a rest mass because they can't be at rest. But the way to think of it, Steve, is that photons will follow geodesics, and these are the pathways through space that effectively to the photon look like a straight line, but they're modified by gravity because gravity is the process of distortion of space. So if you've got a massive object and a photon whizzing by it, it continues in a straight line, but that straight line is bent because the gravitational effect of the massive object is to distort the space around it. I don't know whether that sounds like a glib answer, but that's the bottom line. Photons follow geodesics, which are basically as far as the photon's concerned, are straight lines, but it's the space itself that's being distorted by gravity.
I get it. Yeah.
Good. Now, part two. Rotating black holes are definitely there. They exist, but they're quite counterintuitive for exactly the reason that Steve says. You've got a point with no dimensions. How can it rotate? And once again, there is actually a really good summary of the aspects of black holes. Once again, on good old Wikipedia, if you check out rotating black hole, there is, I think, a relatively digestible summary of what's going on there. And it comes, so the Einstein field equations have solutions, which one of which is the one that Schwarzschild found, which is basically the black hole solution. But there are 4 stable black hole solutions, and 2 of them are rotating. The Kerr rotator is the one I know best, but there's another kind called the Kerr-Newman black holes. And it comes about because these black holes can be described by a small number of parameters. In fact, basically there are 5 of them, 3 of which have 3 components, so there are actually 11 altogether. And this is something very close to my heart, Andrew. It's about something called the no-hair theorem, which I actually wrote about, I think, in Cosmic Chronicles.
From personal experience.
Yeah, personal experience, that's right. And it comes from, let me see if I can find it, because it was quite entertaining stuff.
Don't forget you're wearing headphones.
I know, I'm trying to remember. Can I reach the book with my headphones
I want to drag
on?
everything off the desk.
That's the wrong book.
I did this last week much more effectively, I must say.
No, something
there you
fell
go,
down.
something went.
Yeah, it's nothing breakable. I don't know whether I'd even be able to find this. But it comes from it comes from the early days. The no-hair theorem comes from the early days of research on black holes, and I remember being highly amused by the idea of the no-hair theorem. I can't find it, Andrew. That's a bit sad, isn't it?
All that build-up, Fred.
Yeah. Where did I write about it? It was the. Oh, here we are. One of my favorite. Wait a minute. I'm going to read from the book. Everybody loves black holes, from kindergarten kids to professors of theoretical physics. But until the image a couple of years ago was produced, much of our knowledge was founded on mathematical theorems developed to describe their expected properties. Now we've had first-hand evidence that these theorems work. That was the photograph, the famous photo of the black hole. One of my favorites among them is something with the curious name of the no-hair theorem. And it says that from the outside, the only observable properties of a black hole are its mass, its electrical charge, and its angular momentum or spin energy. All its other characteristics are hidden behind the veil of the event horizon. I might just keep going for a minute, Andrew. The boundary, that of course, the boundary beyond which no radiation can escape. In other words, the black bit. The term no-hair theorem was coined around 1970 by the American theoretical physicist John Wheeler, who commented that black holes have no hair, meaning that all information other than that mentioned above is inaccessible to outside observers. Wheeler actually attributed the term to his student, Jakob Bekenstein, who worked with him at Princeton University. It goes on from there, but basically, it's a the angular momentum is just one of the parameters that describes a black hole, and it is non-zero. And you're quite right, or Steve's quite right, that if you've got a rotating stellar core that is collapsing, then the angular momentum will be conserved, and it will. Basically, the thing will start spinning ever faster, but the angular momentum itself will be part of the parameter list of the black hole. And it's just perhaps our inability to imagine a single particle, a singularity, a single point that has no dimensions, to imagine that rotating. But it does.
Yeah.
Because it's got angular momentum.
In terms of a black hole having no hair, have they checked the nostrils and the ears? Because they are quite old.
Yes. Look,
that's where it all goes. I have this theory, Fred, that as men particularly get older and their hair disappears off their head, it just comes out of here and here.
Yes, I know. Look, I'm far older than you.
Gravity.
Yes, it could be gravity. Yeah. Well, gravity is certainly what describes what defines a black hole. So maybe it is. Maybe there are nostrils and ears, and I'll consult my black hole specialist colleagues next time I see them.
This could open the door to some incredible answers.
Yeah, the no nostril theory. Yeah.
It's not a very good joke, though.
Never mind.
Anyway, thank you, Steve. Thank you, Al. Thank you, Bob, for your questions. Much appreciated. And don't forget, if you've got a question, jump on our website, spacenutspodcast.com or spacenuts.io, and click on the Send Us Your Voice Message tab on the right-hand side, or the AMA tab at the top, where you can send us text questions via email or record audio questions. We've got two ways of recording audio questions. There's also other things you can do on our website. You can check out Astronomy Daily, which updates several times a day with astronomy stories. If you're interested in becoming a supporter of Space Nuts, there's options there for advertising and membership, so check that out. You can read all the reviews, or you can just have a bit of a look around in the Space Nuts shop. It's all at spacenutspodcast.com or spacenuts.io. That brings us to the very end of another episode. Fred, thank you so much, as always.
Great pleasure, Andrew. Thank you. And we'll speak again next time.
We will indeed. Professor Fred Watson, astronomer at large, and from me, Andrew Dunkley, thanks for joining us again. Great to have your company. Keep those cards and letters rolling in. We love snail mail. We might get it in a couple of years. But until next week, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.